To circle the globe 7 times in just 1 second. In 3, to fly to the moon and back. Why, to dash through the starry arms of the galaxy within mere hours. Such incredibly fast journeys will open up to us when we approach the speed of light. But even if you sit down at the helm of a brand new faster-than-light spacecraft, weird and creepy things will start happening to it even before it reaches its top speed. And when it does travel with the speed of light, you'll regret it. In this video, you'll find out, why does approaching the speed of light feel like an acid trip? How did scientists manage to go even faster than that? And why won't you really want to travel almost as fast as light? And we'll absolutely hate it if you beat its speed. In the future, we'll be able to fly over to our colonies on Mars in just 10 minutes if we reach just half the speed of light, 150,000 kilometers per second. No theory in physics forbids it, so what can be the problem? Well, for a start, it'll look bizarre. Actually, I'd like to ask you to move a bit away from your screen to stay safe. Scientists from the Massachusetts Institute of Technology developed this unique video game to help us understand what we'll see and feel when we approach the speed of light. Why does the game take place in a strange village with giant mushrooms and cloaked cultists? Don't even ask. The main thing here is this game demonstrates all the effects of approaching the speed of light, but it doesn't require the gamer to gain speed. Instead, light itself slows down in virtual space. According to Einstein's relativity theory, it's the same thing. With each orb you collect, you travel 3,000 kilometers per second faster. And as soon as you reach just 20% of the speed of light, your surroundings suddenly start to transform. All things in front of you become visibly lighter and more purple. And if you look back while going at such a speed, you'll see a bleak red landscape. What's going on? You're witnessing the Doppler effect, the one that makes galaxies drifting farther from Earth seem to redden and fade, and the ones that are moving closer, like Andromeda, look more purple. At just half the speed of light, the Doppler effect will gift you with infrared and ultraviolet vision, basically turning your journey into an acid trip. And when you turn your head right or left, you'll literally see the spectrums change in real time. Whoa! Although in the real world, outside this cute game, you'll be dead by then. Scientists are used to calling space a vacuum, but in reality, it's not entirely true. Of course, one can't breathe there, but outer space is not empty. And I'm not talking about meteors. Between Earth and the Moon, each cubic meter of so-called vacuum contains up to 10 million atoms, and every single one of them will turn into an invisible bullet as soon as you start speeding up towards Mars. At 20% of the speed of light, the beautiful purple shift won't be the only thing you'll see. There'll also be some lovely explosions on your spaceship's coating. Each such explosion is triggered by a single heavy atom like oxygen. As for the light nuclei of hydrogen, the most abundant atoms in space, they'll pierce the coating and turn the inside of your spaceship into a radioactive zone more dangerous than Chernobyl. By the time you reach half the speed of light, your spaceship will turn into a wreck carrying scorched radioactive passengers on board. On the bright side, a single speck of dust will be enough to end your suffering. At such a speed, colliding with a speck of dust will be equal to a thermonuclear bomb explosion. And while scientists plan for colliding with single atoms is to use protective screens in front of a spaceship, there's no salvation against a cosmic dust particle. So no, you definitely won't be able to travel to Mars in 10 minutes. Unless, at your own peril, you want to try and rush from the borders of the solar system to the interstellar medium now explored by the Voyager space probes. With data from their sensors, scientists learned that a cubic meter there only contains 1,000 to 100,000 atoms, a mere trifle. So, if we make our spacecraft very narrow and then put a conic shield in front of it to protect its coating from many explosions, we might even take our chances in this cosmic gamble and try to go faster than half the speed of light. And then all we'll have left to do is pray we don't stumble across any rogue particle. But when we speed up like this, we'll be in for even more surprising and harmful effects. So, what will we see if we try to reach or even beat the speed of light? For starters, let's go back to the MIT game and collect more orbs. For science. At 80% of the speed of light, the incredibly bright Doppler spot makes it hard to look ahead. It's as if someone burned through the very fabric of space with a giant cigar. But no matter what, you don't want to look back. All you'll see there is an all-consuming blackness following you. You see, at this point, it's so hard for ordinary light to keep up with you from your point of view. It's turning into invisible radio waves. But the most unusual effect of approaching the speed of light will only reveal itself if we turn the Doppler effect off. It looks like a jump drive from sci-fi. Distant objects get even farther away. The view stretches, and you sweep to your destination at a colossal speed. But wait, the relativity theory says it should all be different. Einstein believed that an observer on board a ship approaching the speed of light should see everything in front of them shrink and flatten. Even Earth will seem to be a disk rather than an orb to such a traveler. Yes, flat earthers, your time has come. Einstein is on your side, but turns out he missed one point. According to that same relativity theory, when you're approaching the speed of light, time slows down for you significantly. This means photons from different parts of objects in front of you reach your eyes with a significant delay. That's why the view stretches. But Einstein made sure we never noticed his blunder. The theory of relativity also implies that the closer our spacecraft is to the speed of light, the more it will weigh. The reason is that the energy we use for acceleration sort of turns into mass. Calculations show that at 90% of the speed of light, the spacecraft will weigh twice as much. That means it'll need more energy to accelerate, but this will give it even more mass. Long story short, Einstein is relentless. Whether you're a person or a ship, if you have any mass, it's physically impossible to reach and much less exceed the speed of light. But wait, what about all the news reporting on astronomers and physicists witnessing something that has overcome the light barrier? This faint speck is one of the oldest known galaxies. Scientists estimate it to be 13,400,000,000 years old, but its redshift matches the distance of 32 billion light years. That doesn't add up at all. Apparently, an entire galaxy with millions of stars flew away from us twice as fast as the speed of light, ending up so far away. So why can't we do the same thing? The answer lies in the anomalous behavior of the universe itself. If we expanded evenly, like a soap bubble, we would only see space inside this small circle, the Hubble limit. But almost all the objects we see through our telescopes are 3 times farther away. From the point of view of Earth, as many as 97% of galaxies escape the Hubble limit, as if they had overcome this light barrier. But in truth, this incredible speed is an attribute not of the galaxies, but of the space between them, which continues to expand faster and faster. You see, it doesn't have any mass to abide by Einstein's laws. But neutrinos, which are subatomic particles, do have mass, albeit a tiny one. And in 2011, scientists behind the DOPPLER experiment, working with the Large Hadron Collider, observed a neutrino beam that flew into detectors at a faster-than-light speed of 307,000 kilometers per second. This caused an uproar among scientists, but it was short-lived. It turned out that the scientists had simply fixed a connector of one of the cables a bit too loose. Although astronomers wouldn't care about an insignificant break of the light barrier by a meager couple percent. After all, they've long been monitoring a supermassive black hole in the nucleus of the M87 galaxy, spitting out a plasma jet at 6 times the speed of light. What do you say to that, Einstein? Oddly enough, such faster-than-light jets only confirm his conclusions. In truth, the plasma jet doesn't move faster than 85% of the speed of light, and two things make it look like it's faster: our viewing angle and the illusion of distorted time caused by, you guessed it, one of the relativistic effects described in Einstein's theory. But should we decide to break his rules and try to at least reach the speed of light in our unscientific spaceship, we'll see this: an absolute blackness. It'll last an eternity because at the speed of light, the time dilation effect becomes infinite. In other words, at the speed of light, any traveler will forever be frozen alive in one moment, like Han Solo in carbonite. But is there really no hope of breaking this ice? Seeking to exceed the speed of light, scientists have come up with a few ingenious tricks. But if you try to use them, beware of paradoxes. In truth, there already exists a perfectly scientific method of flying from Earth to the closest star system, Alpha Centauri, in 4 days instead of 4 years. In the mid-90s, physicist Sergei Krasnikov suggested using a spaceship equipped with a special energy drill and tunnel space passages with warped spacetime. This kind of Krasnikov tube will allow ordinary spaceships to travel between stars within hours. But what if we took a superluminal tunnel with us? Almost simultaneously with Krasnikov, in 1994, Mexican physicist Miguel Alcubierre had a brainwave while watching the Star Trek series. In it, the Starship Enterprise uses a warp engine to distort the space around it and travel faster than light. Alcubierre also remembered faraway galaxies that seemed to be moving faster than light and eventually developed a real-life warp engine. The engine uses a special method to shrink the space ahead and expand it behind. The difference in pressure creates a warped space bubble, which theoretically can move even 100 times faster than light, and without contradicting Einstein's postulates at that. You see, a traveling spaceship will essentially stay in the same place without gaining extra relativist mass. So why haven't we built our own USS Enterprise yet, or at least drilled out a network of Krasnikov tunnels? The problem is that as fuel, both of these projects require negative energy. It's a mathematical paradox that currently exists only in physicists' equations. Although one of them, German theorist Erich Lenz, came up with a way of overcoming the exotic fuel catch and created a very similar warp bubble, but he used normal energy. Although there is a rub. In order to speed a spacecraft up so that it goes faster than light, one would have to fuel it with hundreds of Jupiters, and I don't recall USS Enterprise gobbling up planets before each warp jump. However, NASA is quite serious about building a warp ship one day, as long as it can significantly suppress the engine's appetite with the help of new discoveries. At the same time, a group of researchers from the University of Adelaide has spent many years working on alternative solutions to Einstein's equations that would remove the light speed limit, and their first results look promising. So, what will stop us after we overcome the speed of light? Warning, you're entering an area of mind-blowing paradoxes. Here you go, your spaceship bursting out of the eternal darkness at the speed of light and trying to gain, say, an extra 60,000 kilometers per second. But what a shame. After the time stopped when you reach the speed of light, further acceleration makes it run backwards. But that doesn't mean you're traveling into the past. It's just that your superluminal acceleration instantly turns into an ordinary slowdown. This is precisely what happens when you add a minus to mathematical formulas. So, at every new attempt to go faster than light, invariably, you'll end up being thrown back. Instead of going on a faster-than-light trip, you'll find yourself banging your head against the wall. Should I mention that incredible overloads will turn everyone on board such a spaceship into jelly? Actually, there won't even be any jelly left. You see, photons are not simply light particles. Atoms constantly absorb and emit them when changing energy levels. Simply put, photons work as couriers in many chemical reactions. Plus, they help electrons make stronger molecular bonds, and you don't even tip them. So, if you try to exceed the speed of light, these photon couriers will quit, and the matter that makes up both your spaceship and you won't be able to interact with itself. As for what happens next, physicists can't say for sure. You'll either turn into a tiny cloud of dust or explode with the force of hundreds of atomic bombs, or do both at the same time. One way or another, the photon paradox will be the final nail in the coffin of your dream of faster-than-light travel. But what if we try to persuade the universe to allow us a more modest but just as desirable option? Well, if we can't travel at least the speed of light, let's at least exchange instant faster-than-light messages with friends living near other stars. Or is that dangerous too? At first glance, physics gives us quite high hopes. In September of 2022, researchers at Lawrence Livermore National Laboratory in the United States announced they really exceeded the speed of light, this time for realsies. It's definitely not just clickbait. Using a special configuration of powerful lasers, they managed to accelerate photon waves in plasma to 390,000 kilometers per second. That's 30% faster than photons themselves travel. Does this mean we can expect a superluminal Wi-Fi signal in every smartphone? Not so fast. The catch is that it wasn't the photons that went faster than light in this experiment, but specifically the waves of them. It's a bit similar to a water ripple caused by a drop. Even when waves are quickly spreading out, water molecules in them are hardly moving. This suggests that new faster-than-light waves cannot transmit information. The only thing they can do is surprise the recipient with speed itself. Besides, in space, the trick won't work anyway. It requires dense heated plasma. But science does know an odd quantum effect that doesn't care about any of this. It served as the basis for the technology in the Mass Effect game series. Characters used it to communicate at any distance in real time, that is, instantly. An Earth-like exoplanet closest to us, Proxima b, is located just over 4 light-years away from Earth. We are more than likely to colonize it in the future, and while taking an ordinary spaceship there will take a long time, you won't have to wait 4 years to reach out to your friend in the settlement. It's like magic. You open an envelope containing the first part of the message on Earth, and an unknown quantum force instantly opens an envelope with the second part for your friend on Proxima. That happens much faster than light travels, so Einstein really hated such long-distance communication. Anyway, in 2022, the Nobel Prize in Physics was awarded for quantum entanglement for irrefutable proof of the possibility of this phenomenon. If you use it to entangle two particles, then if the first particle changes its state, the state of the second one becomes instantly known, despite any obstacles and distances. But there is one problem. To enable instant communication, two particles have to be entangled on Earth, with one of them given to your settler friend who would deliver it to Proxima B. And finally, measure its state at a previously agreed moment. But the message will only be meaningful if you and your friend agree in advance on what you want to say to each other. Simply put, just opening quantum-entangled envelopes doesn't provide enough context for communication. Besides, when you open the envelopes once, you'll disrupt the quantum bond between them and won't be able to restore it. In Mass Effect, the problem was solved with the help of fictional particles that remained entangled no matter what, but that only created another problem.
I'll make sure this stays just between us.
Thanks, Commander.
I'm kidding. I'll go tell the galaxy what we've done.
I'm afraid I have some bad news for Commander Shepard. You see, a simple chat with friends could have resulted in the Commander unintentionally destroying the universe they were trying to save so desperately. To understand why faster-than-light communication is so dangerous, let's consult German professor Hermann Minkowski, who taught math to Albert Einstein himself. We're going to look at his diagrams, a simplified representation of space and time. The horizontal line is space, the vertical line is time, and the yellow diagonal at an angle of exactly 45 degrees is the already familiar light barrier. To travel from Earth to Proxima B, your friend will take a very fast spaceship that doesn't exceed the speed of light, so they won't cross the yellow light barrier line. But while they're on the road, you decide to use your superluminal transmitter and instantly share your thoughts on your favorite show's finale. From your point of view, the message will only cross the light barrier horizontally. Bear that in mind. But your friend is not happy. They were going to binge-watch the show when they'd reach Proxima, so they used their faster-than-light transmitter to ask you to shut up and keep spoilers to yourself. You might be a bit hurt, but the universe will be so annoyed it'll literally collapse. The thing is, your friend's instant faster-than-light message arrived on Earth even before you got to send yours. But how come it crossed the light barrier at an angle and not horizontally? It's not a mistake. It's just that on board a ship approaching the speed of light, your friend is experiencing the effects of space-time warping we were talking about at the beginning. As a result, the straight horizontal line on their Minkowski diagram really runs right onto the past of Earth. So they'll tell you to shut up with your show spoilers even before you manage to write anything. But if you don't send your message to your friend, you won't be able to receive their reply, which you've already read. And no, you didn't invent a time machine here. You just created a paradox that, as some scientists believe, could destroy space-time itself. Despite its name, the speed of light has nothing to do with light. It's the maximum speed of causality with which parts of the universe are able to interact. And relative to its gigantic size, it is very small indeed. But there's nothing to be done. When we try to overcome the barrier of causality, it's not without reason that we go blind from bright colors, gain infinite mass, and freeze in time with a break in quantum bonds. The universe itself goes to great lengths to protect itself at all costs from the paradoxes that destroy space-time itself. But what if we're more careful? In theory, we could send instant messages to other stars without transmitting any information that could in any way violate causality. That is, we would have to talk about something very general, say, discuss the weather, or grumble about Einstein being right again. But this implies that if we somehow bypassed the light barrier on our own and went on a superluminal journey through the galaxy, we would have to erase the traveler's memories, lest they talk too much when they arrive at their destination and destroy the universe. Tell me, would you want to fly to the stars if you had to sacrifice all the memories of your life?